Alrighty then. That's we're live. Like that's what's going on. Memes here. We are back. Yes, I know. We're what was I gonna say? We're putting the cart before the horse. The whole curvature before the cow. Something like a long story short, we're talking about the quote unquote spherical God Cow yet again. What the heck is this? This is the the interesting coincidence that if you take the concept of the Higgs boson, it is to our knowledge, within generally accepted physics of the standard model, it is the curvature of the Higgs field that happens to be on about the 1 meter curvature scale. So what the heck are we talking about? So let's, oh God, far too many tabs here. So going about doing some different formalizations and everything. Let's go to our old, this guy here. Okay. So as we can see here, let's share with the class. Oh, no, not that one. Oh God, pretend to be a professional YouTuber. Here we go. So what are we talking about? It's the interesting coincidence if you take the mass energy of the Higgs boson, the quote-unquote God particle, whatever you want to call it there. You multiply it by the speed of the light. So basically we're taking its mass, or getting its rest mass energy. Okay. And then we're literally turning it into a spherical cow. How do we do that? We divide by the basic circle thing. 4/3 pi r squared. What are we using for our radius? How about the Higgs Compton wavelength there? It's right there. All right, we cube it. So we got our r cubed. So literally 4/3 pi r cubed just from these current things. And then we're multiplying it by this. What the heck is this? 8 pi divided by the Planck force. So that's the Einstein C4 convention. Yada yada. This is the mass energy induced curvature to space-time, whatever you want to call it. Okay, yeah, ridiculously small number, as we can see there. We got our one Einstein C4 constant over there. All right. When we got all that jazz together, it comes out to be about 1 reciprocal meter, aka 1/meter squared, which that seemed kind of weird. That was not a result I was expecting at all. But it happens to be on basically the human existing level of observers like us. All right, that's fantastic. What does it mean? I don't know. It appears to be the curvature induced by the Higgs field itself. Okay. So yeah, what is this? We're saying the quest for more curvature in this live stream. All right. What the heck are we talking about here? What we're talking about here is if... So long story short is if we do the exact same calculation, except, where is this? All right. So these are kind of different ways to get at levels of curvature. So, oh, that's the difference between the Higgs and that. Let's go over here, and we'll eventually get to a point. Okay. So if we're using the exact same formulation, so basically we're using the Compton wavelength. So that by definition is whatever Planck's constant is divided by whatever mass times the speed of light. So basically you're taking the maximum momentum of that particular thing and you're dividing in there, bada boom, bada bing, it's going to give you out inverse meter squared. As we can see, this number is a lot larger than 1. 9.26 times 10 to the 67. That's freaking ginormous. Okay. This is the exact same convention. Long story short is if you want this to get out to be another number, there's the other way you can do it, where basically you just take the Newtonian gravitational constant. You multiply it by your mass 1 times your mass 2. In this case, we're assuming the maximum element of mass that we know to physics as we know it. Unit mass. And that's the Planck mass. All right. So we got a big G, mass 1 times mass 2. So we're just taking the same value, squaring it. So we got effectively mass 1 times mass 2. And we're dividing it by our r squared. What's our r squared? That's our radius. So we're literally just plugging in Planck units. And when you do that, you're going to end up getting out. Sorry, I'm jumping ahead. You're going to get, perhaps no surprise, this ginormous number, which is essentially, it is the Planck force. It is the maximum unit force that we can have in our realm. It is the literal limit. Okay. So what was that other thing we had up there? We go back. We're dividing it by h bar c. What the heck is that? That is essentially the bending stiffness of space. I ain't no genius. I just literally know that Wolfram Alpha told me. It's our interpretation here. Interpretation. Bending stiffness. Or there are others, as we can see. Inverse distance potential coupling constant. Contact density. That sounds pretty good. Image potential energy gradient. Hey, DL. Good to see you, my friend. Good to see you. Welcome. Now we're just going over some stuff and things and some interesting coincidence. Okay. So basically, if we just go back and we divide it by that, we get this ginormous number here. It's like, what is this ginormous? 3.8 times 10 to the 69. Inverse meters squared. What could that even be? Well, it's an inverse length. Okay. So the claim would be is if we're doing this similar setup there, because basically you can do this with the Higgs mass. So far too many tabs here. Okay, so oh, did I get rid of that there? Oh God, so neglected. Oh, yeah, we'll just go over here. So literally, here's what we'll do. Well, don't mind me and my modifications. Let's just go over to this guy. So let's just do the same. Let's just do the same thing over here. Let's just take our little formulation. We're literally just going to switch it to the Higgs mass. And then we're just going to do the Higgs Compton wavelength. Okay. Oh. And look. Again, it's slightly different because we don't have like the full Planck force and stuff. So we don't have like a little 8 pi and everything like this. Yes. Welcome, Rick. Thank you for lurking, my friend. We'll get into this stuff. We're just doing a quick review about just what the heck we're doing. So what are we claiming here? We're claiming that if you have the curvature induced by a Higgs boson's mass. So we got mass 1, mass 2, divided by our radius squared. And we're using the Compton radius, Compton wavelength, which according to Professor Carroll, is basically the magnitude at which particles have their particle-y nature, or we could define them within that, because maybe there's some squidging, maybe there's some uncertainty for whatever reason or not, but that appears to be a thing. And again, it's interesting that it appears to be a little over about 1 meter squared, or 1 inverse meter squared, which is interesting, but it's right in the ballpark of what we were looking at before. All right, so why is it 1? If we go back, what does it actually compute? It computes. Basically, it gives us this number here. It's like 10 to the 26 minus 26 newtons. Newton is the SI unit of force. Okay. Why is it coming out to be 1? Well, if you use that h bar c, Planck's reduced constant, times the maximum of speed, the speed of light in a vacuum, because we have to say that. That it apparently is not a true vacuum. It gives you a number like the same 10 to the minus 26 magnitude. The number's a little different. Long story short is the number is slightly above that. Therefore, we get a little bit over 1. Okay. Big whoop. What does this do? Okay. So coincidentally, when we were having our Saturday discussion with folks at the physics monastery, uh, at one point we were talking about, and I think I had just gone through like this little derivation here or something, talking about a surface, and then Echelon had brought up. He's like, it just makes me think that maybe there's if we could have some information because backstory Echelon, he basically has been a programmer. He's like an OG programmer from back in the day when large banks would literally have like 2 megabytes of RAM to run their entire ATM network. Okay, that's a crazy thing. Uh, memory for those of us that have been following has gone up astronomically in the meantime. What does that actually mean? You can play around, and if things aren't as efficient, it's all right. We got brute force computation, and wow, some may say it has led to. Again, I'm not a programmer, so I don't think I can fairly say, but I've heard folks say things like "quote unquote" spaghetti code and stuff. Like the code isn't necessarily as efficient as it could be, because back in the day, you only had so much to work with. If you have a very bountiful stuff and things, you got more leeway. Okay. But Wade says, well, maybe this is some informational context or something. So that got me thinking because our friend Bill from the Gravity for the Masses YouTube channel, he's been working on more of a thermodynamic method and stuff, and some of it does seem very interesting and stuff. Precisely what it means, don't necessarily know, but it got me used to performing computations of that nature. So I'm like, wait a second. We're saying we have an induced curvature of this scale. This is a really big scale. What is this scale? It's literally. I mean, maybe it shouldn't be much of a surprise, but if we multiply it by the Planck length squared, oh look, we get 1. We get unity. Why? It's the inverse Planck length squared. It just happens to be at a maximum, which, for me, this at least is a stronger justification rather than just being like, well, the meter is significant, so thereby we can just flip everything on its head. This seems to, rather than just being like, all right, because the thing is, if you're going to say there's a minimum and then therefore is a maximum, okay. If we are going to say that, you need to choose whatever the central point is. Now, I could just say I'm going to reference the meter and just do 1 over that. That basically has a preferred unit basis. Maybe there is something very special about the meter. I mean, when you see the Higgs scale coming about approximately about 1 meter squared, it's like, maybe we shouldn't be surprised because, well, if that deviated too much, probably observers like us wouldn't exist. So it's a bit of a anthropocentric argument there, but we're literally just taking constants of nature. We're just doing the same thing for the Higgs, and we're just assuming, all right, well, what if we took the maximum unit mass separated by the minimum unit radius, and we took a look at the bending stiffness of that? Well, it appears you would have curvature induced at a ginormous scale. Well, if there was curvature induced at a ginormous scale, what might be going on? Is there something we could glean from this that might be interesting? Okay. So if this is 1 over meter squared, what is the magnitude of this relationship? Okay. Let's do a little trick here. Rather than doing this, let's take out reciprocal. Let's just take that as a straight up area of the curvature induced by the Planck mass, given our convention there. Okay. So if we do this, let's see. Oh, wait, this is That seems to be kind of close to right about the radius if we assumed literally direct invert. It's really close to basically if you assume a 4-dimensional hypersphere with literally utilizing the inverse Planck length. Okay. But that's not what we're talking. There's so many rabbit holes you can go down there. Hey, Poindexter Bill. Yeah, we're just talking about it. So, but here's what we're gonna do. So we're gonna go to our old friend, the Bekenstein-Hawking. All right. So as yes, I may or may not visit this place often. So, but basically, this is the Bekenstein-Hawking entropy formula. So basically, the claim is that if you take this, you could calculate the essential thermodynamic. And again, this is for a black hole. So again, there are certain assumptions here. The claim is we're applying this to the curvature for our realm, utilizing the maximum unit mass, the Planck mass. It gives us an area curvature. Let's plug it in and see if it can maybe help answer some questions we've been having. Because I just remember when Echelon brought that up, he's like, "Oh, well, maybe there's some information correspondence with that area or anything." I'm like, "Well, I know Bill's been working on this, and it's given me a chance to go through some of these calculations myself. So I'm a little bit more familiar than I was before about these. Let's do a calculation." So what's this? This is Boltzmann's constant. All right. This is basically the thermodynamic. Long story short, anything with temperature, you basically need this. So it's about the potential microstates and how they could reconfigure and everything. All right. This big A is the area. Okay. So we've got a constant. We've got a proposed maximum area of curvature. And then we divide it by 4 Planck length squared. So basically 4 Planck areas. Okay, cool. So what do? We take over here. Okay. So this is the area of which, according to our calculation, we would have induced curvature over. Okay. So we have ginormous number, 3 times 10 to the 69 square meters. Okay. So we throw that in. We got our Boltzmann's constant there. We've got our area there. And we got our 4 Planck length squared. So we got our 4 Planck areas. Okay. Gives us these numbers. Okay. Now, it's giving us these things. And again, speculation. No. Totals. Hold on. Let me get Stephen Wolfram in here so we can cover our butts because we're totally speculating. Here we go.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper-Rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyper-Rulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
So yeah, Bill, I do the same thing. This is not in joules. This is in square meters. That's the thing. I do the same thing a lot of times. I'll go back and forth and I'll be like, "Oh, I recognize that number." And then sometimes it takes somebody pointing out to me, "No, that's not what that number is," just because I get so conditioned to seeing that number. This is in square meters. So when we put it out there, it's giving us a conversion factor. I'm like, this many joules per Kelvin and everything. And I'm like, wait a second. Like, Echelon brought that up. I did that quick calculation. I'm seeing numbers. I'm like, I haven't seen these numbers before. These are new to me. I'm sure other people have seen them before, but I'm like, oh my God, I haven't played around. And some things kind of really seem to line up because I could do that other little calculation. It's like, all right, I can calculate what 10 to the 61 kilograms of a mass energy bank for universe or whatever, you run into a major problem. Okay. At that point, you're like, well, how big is our realm? Because if you're going to incorporate the vacuum energy density, that's like, it's about 3.5 giga electron volts per cubic meter. It's pretty small, but it's not zero. That's why some folks, you'll hear certain terms like, oh, 0 point energy or something. What does that mean? It's like, when we take all the stuff and then we like pump out all the air as best we can to create a vacuum as best we can, there's about 5 times 10 to the minus 10 joules per cubic meter. Why? Okay. Long story short is, if I take in that other calculation for mass, and I'm going to say, long story short is, I get about 3 times the maximum size of our current observable universe. Again, that's 1,000 times larger, but you kind of run out there. And if you're going to make the claim there is a maximum extent, either the energy density is going to keep on falling, maybe an alternative analysis, maybe we're just in a black hole, so if more stuff is falling in, you're just going to keep on continuing to expand out, but then again, there's still like a factor of 2 there. For every Planck mass you get, you extend your radius by 2 Planck lengths. Radius, not diameter. That's why it seems to go up by like a factor of 4. And that's why, like, a supermassive black hole has like less of the density of cotton candy, whereas at the Planck mass, it's ridiculously dense. Okay. Again, I'm not purporting to explain why that's the case here, but this was very interesting here. So, let's see. Oh yeah, Bill. It's because basically, if you take the dark energy and stuff like that, I think if you do like c² or whatever, you'll get like 10 to the minus 18 or like 10 to the 18 seconds or whatever. Because if you do basically c or c², you'll either get a length or a time there. So it's you either like multiply or divide. It's something like that. So you can just go back and forth. And again, a lot of this is different perspective. A lot of times I'm like, oh my God, this is fascinating. I realize, oh, this is just a definitional thing. This is just the case. People point that out to me and I'm like, oh, well, it's new to me. But this was some things here. So I'm like, all right, we got some numbers. All right. And you can put in different temperature. You can put in 1 Kelvin, you can put in like the cosmic microwave background. I'm just like, well, if this is basically inverse Planck units in meters, I'm like, well, what could we throw in? I'm like, well, if we want energy per temperature, let's just throw in the Planck temperature, the maximum of temperature. Again, it's probably just a reckless thing to do. Probably doesn't make any sense, but it gave me some numbers with some significant digits, which, I don't know, if you're looking to attempt to do some computations, you really need at least 4 or more significant digits to try to see if there's a pattern there. So let's take a look. This is a ginormous number. What the heck is going on? Okay. So, long story short about my other tangent there is, okay, I can do a calculation for like a mass allowance for mass and energy, but I'm like, it was nowhere near enough to account for the vacuum energy if you're going to assume an additional like 8 orders of magnitude over what our observable universe is. It's like, I can't account for that. Basically, I've got a cool number. It lines up great. But how do I account for the rest of the configuration of whatever fields and or stuff and things that is giving form and apparent persistence to our realm? Long story short is I think I needed 10. This is more than enough. This is more than enough. It should actually help account for some other things. Okay. So what is this number here? All right. Get this ginormous number in joules. Okay. So again, if we swapped it over to kilograms, it's about 8 times 10 to the 130 kilograms. How much mass is that? Oh, it's not an energy density. It's about like 80 times the magnitude of, I think, the estimated mass of the observable universe, because they have like, it was like 10 to the 53 kilograms or maybe joules. I'm give or take a magnitude. Hold on, was it universe total mass? All right, so about 10 to the 54 kilograms. All right, so we're like, yeah, about roughly about 80. No, almost 100 magnitudes off. Wow, that's a lot of mass, man. Okay. How can we try to quantify this in a way that might make sense? This is a ginormous number of joules. I'm like, all right, well, let's look at it in a different form. Let's look at it in Planck energy. Divided by Planck energies. Okay. It gives us this number here. Does this number look a little familiar? So coincidentally, let's take this number. Let's grab it right here. Go over here. Okay, there's a couple modified equations there. All right. So, actually, before we do that, let's do Planck length. All right, so the fourth. Okay. So let's take that. Let's multiply that number. Oh. 0.25. It's kind of interesting. So apparently, that number, go back, we divide, oh, wait, I mean, shouldn't this appears to be, I wonder why it's coming out with this. Well, because we divided by 4 Planck lengths squared. Because we could also do, what is it? All right. So we partitioned it by 4. But the interesting thing is, all right, we got that number there. Let's go back. Let's do a little play. Let's take the square root of this number. Actually, we should probably take the 4th root. Let's raise it to the 1/4 power. Okay, the 4th root. Okay. Gives us a number here. Let's take this number. How does it compare to the Planck length? Oh, 7.071 meters. It's kind of close to 1. What's our modifier? Let's search for a dimensionless number. Let's get more. Oh, look. It looks like the easiest answer. That's just 1 over the square root of 2. Oh. That's kind of cool. It's almost like it's supposed to be there. All right. So now, and again, this is a crazy thing. What am I saying? What are we literally saying? It's like we're taking the maximum of curvature defined by the Planck mass. So the maximum unit mass divided by the minimum unit length, both squared, times the Newtonian gravitational constant of proportionality. Okay. Gives us an induced curvature radius. We're plugging that in to the Hawking-Bekenstein thing, seeing the consequences there. And then we're multiplying by the maximum of temperature. And again, I have no idea if that's a thing. This is why it's a theoretical research exercise. We're exploring with the folks here and everything. So, okay. So we've got that energy. And again, It does seem to have some proportionality. It's literally 4 times the Planck length to the 4th, but I mean, we literally put that in, right? We put in the 4 right there. Because if we just took that out, that should just give us... Well, this is the inverse Planck length squared. I mean, we got another 2 dimensions of length there. That's going to give us 1 over the Planck length to the 4th times the Boltzmann's constant and stuff like that. Okay. Yeah. This literally should be Planck length to the 4th. Yeah, 1 meter to the 4th. Boom. So, and again, I guess you would expect these things to come up. Is this actually reality? I don't know. That's why it's a toy model. We're playing around. We would see what the consequences would be. And again, we're utilizing constants of nature. Trying to play around. We're trying not to insert too many unnecessary things. We're trying to avoid epicycles. We're exploring to see if we can use these interesting coincidences. And a lot of this was, to be fair, if the curvature induced by the spherical God Cow or whatever, if it wasn't pretty dang close to 1, and then if you divide it by the vacuum energy, and then it happened to give out about the same magnitude as the cosmological constant dimensionless. So let's actually just show what we're talking about here. Okay, I think it's one of these guys. So let's just steal this. Oh, no, we need this guy. Okay. Go over here. Tab. I know, a bajillion tabs. So long story short is, you take this crazy number here. All right. Again, it ends up being basically pressure. So as we can see, it's that much greater than the universe vacuum energy density. Okay. The interesting part that I found is when you take the universe vacuum energy density, you divide it by that spherical God Cow. You get about 1.1 times 10 to the minus 52. Okay. So, again, it's just, that's a dimensionless number. It's a ridiculously small number. WTF, mate. Okay, the WTF comes from, I'm going to say, this number looks a little familiar. What's the magnitude of the cosmological constant? About 1.1 times 10 to the minus 52 meters, reciprocal meters. So basically, it's that number divided by meters squared. 1.1 times 10 to the minus 52. 1.1 times 10 to the minus 52. Again, this is a dimensionless number. So that's just its magnitude to the measured vacuum energy. Just that's the magnitude difference. Okay, this says reciprocal square meters. And this is also something that can be kind of confusing sometimes because this whole 8 pi g and everything like that, like 8 pi g divided by c raised to the 4th, this is 8 pi divided by the Planck force. Because the Planck force is speed of light to the 4th divided by the Newtonian gravitational constant. Because it's just going to come out with dimensions of force. Just 'cause, well, that's 8 pi divided by the Planck force gives you the same thing, the Einstein C4 convention. Because the Planck force is, I raise to the 4th divided by big G. I might need to notate that it's a unit. Okay. So again, it gives you the Planck force. Because that's what it is. All right. So, all right, big whoop, big whoop. So the weirder part, or maybe not so weird, note this, because when you multiply it by Planck force, or the Einstein constant. Let me do the 8 pi over that, just because there's a couple of Einstein constants, so sometimes if you don't specify, you'll be in one dimension and be like, oh, why is all the numbers all different? So, force. Okay. Okay, so the weird thing is, all right, so then when you take this whole spherical God Cow, you multiply it by the Einstein C4 constant, it gives you, and again, there's of magnitude, there's a little bit of rounding going on there, full disclosure. It's giving you about 1 reciprocal meter squared. That 1 reciprocal meter squared is the units of the cosmological constant. Okay? So when we multiply by that, we get about the reference dimension of measure. And when we compare it to the vacuum energy density, we're getting the magnitude, and then if we multiply by that, then we're going to get this. One has to be careful, because, to be fair, you can plug in any mass number here, and just because if you're going to be using a Compton wavelength, Planck's constant of proportionality, like, you might get a much larger or smaller number than this, utilizing something other than the Higgs boson. But the trade-off is that once you multiply it by this Einstein, this C4, Einstein-Copper convention, whatever you want to call it there, you'll get a number that deviates from that approximate 1 reciprocal meter. But the thing is, if you multiply your result from that by the other one, you're going to end up getting, long story short is, if you're dividing, because like this is the vacuum energy density, because it says it right there, this little rho lambda there. Long story short is, if you're dividing something into that, and then you're multiplying by that Einstein constant, it's going to come out to be this, because one, you're dividing a thing, so you're dividing by spherical God Cow. The other, you're multiplying by spherical God Cow. Spherical God Cows come together, net out, and then you're just going to get whatever the cosmological constant is. The interesting thing, for at least an observer like me, is the Higgs boson, and again, using this convention, does seem to be the only mass term that comes out to basically have this magnitude within the dimensions, and when multiplied, does come out to be approximately about 1-ish in magnitude for the units required. That seems a little strange to me. Like, why is it coming out on the meterish scale? Does the meter actually have some meaning, or is it just observations from flush bags like us that might be going on? Okay. Let's see. What do we have here? All right. See, Bill, that's a good thing there. That 122, I mean, if we're going to go about the observable universe, my thing is, I'm like, okay, that's what we can see, and apparently we keep on seeing farther back. I'm just like, let me just take some numbers, assume we haven't seen all of our realm, and try to see if we can go to the maximum. What could we get? Why? Because I am a very reckless person. So, that's what we do. Yes. Blankety blank blank. Do I think math is discovered or invented? Yes. That's the best answer that's literally the answer I give when I get asked that question. Yeah. Okay. So let's not bury the lead. Let's not bury the lead. Okay, so we've got this here. So let's take a look at some other things. So we divide by Planck energies, and all right, we're like 1/4 of the length scale there. But what can we do with these energies? Is there something interesting that's going on? So let's continue. Now, let's take a quick moment. And we'll, let's do another little equation here. Okay. So what we're going to do is, here's the original thing, how I gone about and calculated quote-unquote mass for our realm. And again, there are assumptions baked in, so we're assuming this is something that I heard from Dr. Salvatore Pius, as well as Rick DeWitt. Something along this range, but if you assume the Planck force, which was a constant, hold on, let's, how do we do it? Mass energy of universe. All right, so if we just do mass energy of universe divided by radius of universe. I'm using lowercase u because who knows what's beyond our realm. Maybe there be dragons. All right, you get this number here. That's a lot of newtons. Okay. Oh, it looks to be about the magnitude of the Planck force. All right, well, let's divide it by the Planck force. What do we get? It's like 25 something. Okay. We get this little number here. What might this little number be? Okay, let's look for some closed forms potentially. All right, all right, got some potential things there. I can't really parse that. Let's look a little bit over here. All right, so 5 over planet 4, blah, blah, blah. Okay. And again, we don't necessarily know because we only had one significant digit of information there. All right. So let's not bury the lead at what it most likely is, because what it most likely is probably gonna be about 25, 24 or something. Long story short is it looks to be about 8 pi, aka what we use in the Einstein cap convention there. Because if we do this, let's do again, only one significant digit. It's of magnitude the Planck force there. Okay. So, but again, we're not even including this. We're just trying to do a rough estimate about what might be going on. So if we kept that, or the Planck force, if we assume that was a constant, here's what we do. Force, set that equal to, we're going to solve for kilograms. So we're going to look for x, kilograms. We're going to multiply by the speed of light squared so we can get an energy. We're going to divide it by a radius. And we're going to claim that radius is meters squared over the Planck length. So basically 1 over the Planck length, and we're squaring meters. So we're squaring 1 to get an additional dimension, this dimensionful hack. Planck length. Don't need all caps. Planck length. All right. Boom. Compute. So all we're doing here is we're going to assume that for our realm, this space-time, this whatever you want to call our realm in which we operate and exist, if we assume that the Planck force is generally going to be about a constant throughout it, we should be able to, if we could specify one of these terms, either the mass energy or a radius. So again, taking a hint from Thad's work, well, if there's a minimum, then there must be a maximum. And then if universe doesn't necessarily go on to infinity in the normal sense, I mean, if it's a sphere or a circle, a hypersphere, whatever, I mean, to be fair, you might just be able to keep on going for perpetuity. That's might not be the infinity that some folks are looking for, but it's an infinity in a different context. So we may have infinity within the realm of time, so to speak, because we might have cycles, and to be fair, you go around a circle. You just keep on going. That is one form of infinity. It's why also you'll see like a figure 8, because it's the infinity symbol just keeps on going. Okay. So when you get those numbers there, you get, okay, God, look how big this is. Look how ginormous that number is. Okay. So we can open that number and we solve for kilograms. Okay, so what is this? 8.33 times 10 to the 61. All right. So, seeing as we did not have that many digits of precision, this is probably a good rough bet. We'll truncate it after the fourth significant digit. That's about all the information that we really put in there. All right, so now we have 8 times 10 to the 61 kilograms. Okay. What's interesting about that number is we just went over here and we tweaked this. We literally, let's do this. We're going to take out that square. We're just going to relate the meter to the Planck length. We'll square it. And now we get dimensionless range. Wait a second. 3.828 times 10 to the 69. That looks familiar. Oh, wait, this is the first number that we had. And here is where coherence starts to potentially be able to tell us some things. We got that number. Okay, so let's just multiply it by the Planck mass. Oh, look, we got that 8.3 times 10 to the 61 kilogram number. Oh. Well, that, maybe that's why it took me a while to realize. And again, this is why I say it's a toy model, just because whatever you're doing in it, you can do some calculations. Does it mean it's right? No. Again, we have baked in assumptions here. It almost seems like we're using the meter as a balance point, and again, that seems weird. Now you could maybe justify it's like, okay, well, yeah, hey, the density of 1 cubic centimeter of water is 1 gram, 1 cubic in again. At our human, above sea level, at 1 standard atmosphere, it's a little bit shy of 1 gram per cubic centimeter. At about 1.5 bars, at just under 4 degrees Celsius, it is precisely, or it has the range there. Or if you take most water, which probably isn't much above sea level and is probably a little bit underwater, it's an argument. It's an argument. Or you could say maybe, well, the curvature induced by the Higgs appears to be about 1 meter, so maybe we should use that as the meter. Then again, we only have so many significant digits. Our confidence is about 3 significant digits. And then we kind of argue about the next 2 that we have reporting, and we're getting better and better measurements. But I'm like, all right, irregardless of that, I can say that because Massachusetts, and again, congratulations to the Seahawks. You played better football. You played better football. We had a young team. Seahawks earned it. What am I going to say? All right. So we've got this number here. Now, why did I go through all that? Just to show this might be a little bit of coherence here, because this other number, well, this is an energy. So we need energy. All right. So why am I showing you this energy? So, if we do that calculation, let's just go back here. All right. Just take this number again. We'll give it the last 2 digits that we had. And now we're just going to multiply by the speed of light. C squared. Let's give us. All right. Let's give us an interesting number. Why is this an interesting number? It's giving us 7.488 times 10 to the 78 joules. That is a lot of energy. And you can even see here, let's say blah, blah, blah. Lots of stuff. But, okay. We've got that number. This number actually did look familiar. Because when we take this number and go over here, let's just take a look at another random combination of Planck units. Take the Planck mass again. But this time, let's divide it by the Planck time squared. Okay. We got the Planck time squared divided into Planck mass. Wait a second. Wait, hold on, wait. 7.488 times 10 to the 78. Wait a second. let's duplicate this and let's just so we can go back and forth. All right. Wait a second. 7.488 times 10 to the 78. 7.488 times 10 to the 78. WTF, mate? What's going on here? For those of us that are paying attention to the units, again, I did not say the units. This is essentially the Planck spring constant. Why? Not that I know, it's just literally what it says. The dimensional framework is mass divided by time squared. All right, something, that whole spring equation that you had there, and you're like, wait a second, it's going a distance. I'm like, but doesn't it net out a distance over a range of time? Because we're assuming spherical cow or a cubical spring or something like that, where basically there's no friction and everything, and basically the only thing that seems to matter is an oscillation period. How very interesting. Okay. So what's the whole difference between these things? Okay. The answer that you get is, maybe shouldn't be all that surprising, because it was the answer we injected. 1 meter squared. Playing with this toy model, it pops out a lot. Now, again, for many of these derivations, that just, for like this thing right here, or the derivation that we just did with that Planck force, we literally had specified 1 meter squared, because we were taking literally meters squared divided by the Planck mass to get those units and everything. So we baked that in. Now, again, one of the reasons I'm exploring these things is because, okay, I can do that, I can bake that in, but when you start getting similar numbers for that, let me just go back, because, well, we had that number, and that number was based upon this number. That number we seem to be able to just derive based upon the maximally induced curvature for the maximum unit mass within physics as we know it, the Planck mass. Okay, so we're literally just doing good old Newtonian gravitational dynamics. The Newtonian gravitational constant or proportionality times the maximum mass twice. Mass 1 times mass 2. We got the 2 there. And then radius squared. A minimum of length. And again, you could argue about this. Maybe this is off by a couple of factors of 2 pi or something like that. But it's at least getting us into a ballpark that we're getting this number out. And again, it's in reciprocal meters. And if anybody's thrown together and looked at some of the dimensional ingredients of a Lagrangian before, you're going to see things like this pop out. There's also a reason why all good physicists sets h bar equal to c equal to 1. Why? Oh God, it removes so much clutter, but perhaps within the dimensional clutter, we may be able to get a better idea of what's actually going on. And again, I'm not a physicist nor a mathematician. I'm a crazy person that pretends to be a science explainer on the internet. But every once in a while, crazy people notice things too. Not saying this crazy person, but maybe some of the folks that are watching now or temporally in the future may have interesting things to share with the rest of us. Let's see. I'm talking about both so that superposition thing. One of the reasons I did that video the other day is just because I'm like, there's somebody said it was like, was the fattest Schrodinger's cat or something. Or it was a chunky Schrodinger's cat, and I'm like, I think I have a picture of a fairly chunky cat, literally half in and half out. So I'm like, it's an adorable picture. So I felt I chose to use it. All right. Let's see. Hey, golly! What's going on? How we doing? All right. Density is a scalar. Oh, that's See, See, that's an interesting thing. A lot of times it's, I don't know. Hey, that's why I'm like, is inflation a thing? I don't know. You can make that. It's like, it depends upon what assumptions we're baking in. And I think a lot of times people get confused and often just don't listen to each other because they have an idea that's very clear in their head and they just start sharing it. Without the context, people are like, yeah, I don't know what they mean. Oh, that doesn't make sense. But if you're like, we are working within a holographic principle, we assume that the dynamics within a black hole or some X hyperdimensional surface will apply given this context. Or you could say, universe has always been here, it will always be here, and we are just flowing within the cycle of our realm, and it's just going to continue to persist and do different things, and then we're living in just one of the infinite potential number of worlds that will end up cycling at some point, or maybe it's all happening everywhere all at once. These are different perspectives. So that's why I think very often you kind of got to quote in. This is something, God, I learned from my friend Jen a long time ago. What are your axioms? Because I'm seeing things here. We're talking about matter and antimatter. I mean, heck, even on the call with some of the Mystify Sci folks, even on Sunday, some folks were bringing it's like, oh, is antimatter a thing? It's like, well, are we getting lost in the math? I'm like, well, I'm pretty sure, like, initially, like, Dirac got those negative answers, and he was like, he just ignored it because it didn't make any sense. Because it's saying it's like an antimatter. And then when you detected something that looks a lot like the electron, but seems to have the charge of a proton, it's like, oh, that seems to be antimatter. What is that? Oh, it spins the other way. If you spin the other way, everything else is intrinsically the same. The only difference is the charge. So I'm like, I'm pretty sure that was an observational thing. And again, depending on who you're talking with, some folks are like, no, we haven't observed this. Or I have questions about this. Like, I know Anastasia and Shiloh have brought up Kirchhoff's law, Planck's black body radiation law, and okay, they brought up some things. And again, doesn't seem to be an easy thing to do here on Earth, but it appears that they're having experiments that have shown certain things there. And then you can argue about, well, how close is it to a perfect black body? And then do we get into the no true Irishman thing? I'm Irish, so I think I'm allowed to say this. But basically, it's like, well, is there any true black body? It's like, oh, the cosmic microwave background, again, assuming that we actually measured some stuff and people weren't just like, oh, we didn't account for water from the Earth. Again, I am assuming that the vast majority of science, as we typically understand it, is probably pretty much all right. Now, we may require alternative interpretations. Like there may exist an interpretation for like what we have that all of a sudden it comes around and all of a sudden we're like, duh. There doesn't seem to be a publicly available explanation like that right now. So I'm just operating with what we generally know, and if I'm going to cast my doubts on something, I'm just going to straight up say, I have my doubts about this. Here are the reasons why. Yeah, but you're right. Why would I throw out the whole thing? It's like, you can argue about this or that, but the sheer fact it's like, all right, people have the ability to remotely view this broadcast from across the globe, potentially in space. Some people don't think we've been to space. Hey, that's fine. But it's, I don't know. Planes seem to be a thing, and I don't know. Maybe it's all a lie. Maybe it's all a psyop. But I tend to think that I think we've done a lot of very cool things. The sheer fact that this even exists, I could do this on a calculator or something, is totally fascinating to me. I was talking about attracting. Yeah, that might be like, I mean, again, I'm kind of looking at a lot of similar things there. I personally think that maybe there are some other things, and again, I'm trying to work with that. And again, we do have modern AI agents and tools, and actually Wolfram Notebook assistants that we can kind of go through and different stuff. But yeah, people are free to their own opinions and interpretations, and heck, we'll let experiment guide our path. All right. And then we can argue about the experiments. Okay, so we've got, what is this? Oh, where were we going? Okay, so let's go to, where was this? Okay. So we got that finally total mass energy. Okay, so we got this many kilograms. Let's do c squared. We got our, so basically this is a calculation I had done for, to calculate the mass energy bank of universe, assuming that Planck force thingy. Okay. So that's a very big number. All right, so we get this number here. That's a ginormous number, but it's not quite as ginormous as this number here. Okay. That's a lot more joules. So my thought is, well, that was the number from a calculation, basically assuming a lot of the same things. Here's a calculation from a different perspective, taking more of the informational perspective, assuming if we had all the information and a maximum boundary of curvature at the maximum temperature, how much energy would our realm have? Well, this allows, this is plenty of information, energy I would claim, in order to set up not just a mass energy bank of the universe, but the actual field configuration. That, in my mind, was, I hadn't gotten that far yet. I kind of like, oh, I need to do this at some point or other. Echelon brought that up, and I'm like, I have some experience looking at going through some of Bill's stuff, and he's been talking about this for a while, so I'm like, all right, let me apply that. I'm like, oh my God, I haven't seen these numbers before. And again, this is a theoretical calculation. I'm not saying that this is the territory. I'm just attempting to make logical inferences that we can back up with generally accepted science, like constants of nature and stuff like that. And again, people can argue about that. But things that we have that appear to be constants of proportionality in our realm to what's going on. So I hit enter. 9.57 times 10 to the 68. Well, that's a number. I got a couple of significant digits. Let's see what this looks like. Let's do this. Take square root. Okay. So let's take a look at it in reference to a couple of things, because now this is and again, this is a dimensionless ratio. This is the dimensionless ratio. What it actually means, I don't know. I just look at between ratios of other stuff. So that's a big number because we divided the smaller number into the bigger number. Look at ratios of Planck length. This is one of the interesting things. Wait a second. 1/2 a meter. So that would mean that if we did 2 Planck lengths. Oh. It seems to be at 1 meter. So again, that's just because it's a unit of length. If we divided it out, it's basically going to come to 1. So as unity at 1, I'm like, I mean, I honestly just didn't recognize that before. So I'm like, wait a second. A factor of 2? Why is there a factor of 2? Well, I can't say, but I'm pretty sure for at least the simplest solutions, the Schwarzschild solutions, for again, a non-rotating black hole in its simplest form. And again, as far as we know, any black hole things that we believe to have observed, they're all Schmitting. So you need something more like a Schwarzschild black hole and include angular momentum, aka spin or whatever that may or may not be, as well as charge. But at least for the minimal formulation. To be fair, most of the other metrics are just kind of built upon this. They just have like more square roots and stuff like that with the factors of like h bar and elementary charge or Planck charge or something. I went through them before. But formula. So if we just take the basic formula. Okay. The interesting thing is, wait a second. For the event horizon radius of a black hole, okay, gravitational constant, your mass constant, c squared, those are it's 2. As a factor of 2. Now, at first, the way this is written, my mind just reads linear. 2 gravitational constants. Gravitational constant is gravitational constant. What are you actually feeding in? You're feeding 2 masses. See, this is why for every Planck mass of a black hole that it increases by a factor of 2 Planck lengths. And again, I'm not an expert in general relativity. That's Sir Roger Penrose. But for me, I'm like, well, that's kind of interesting. Why is there the factor of 2? Apparently, it was necessary to make it work. I'm like, okay, well, a factor of 2. We'll get that factor of 2 Planck lengths. We seem to get a level of unity there. Why that is there? I haven't got yet, to be fair, I haven't gone through. This was literally something from, I think, Saturday evening going through into Sunday that I started to investigate, and I haven't gotten down to the bottom of it fully yet. I'm sure there's an easy explanation right there. But also, this is something where the AI agents and stuff come in, because it's like, all right, I can spend all this time, and eventually I'm like, oh, this is where this factor of 6 came from. Oh, this is this. And then I'll throw the question into an AI agent, and I'll have chat go through it, and I'll be going through the calculations, and okay. I figured it out. And I'm like, I checked the answer that I'd finished putting out like however many minutes or an hour ago, and I'm like, okay, yep, it simplified everything I had and did it a lot faster. Just because if it's just a standard algebraic manipulation, if it just needs to follow rules and look to see what the modifier is, it can tell that quickly. But again, actually going through, doing it yourself, it's like, okay, you kind of feel, and again, I'm not doing it by pen or paper there. I mean, Casey's gonna lose his mind. Oh, that's not math. I'm like, hey, just using a calculator. I'm using it as a calculator to do some quick little calculations to help an observer like me. Okay. So I thought this is basically to the extent I'm at. Again, feel free to use any other intuition or stuff, but my thought is, I'm like, well, it's probably going to have to reformulate this anyway to calculate, because what is it? A lot of times they'll say geometricized units, which is Planck mass to the 4th. That's what we assume. So I'm assuming when I go through and do those calculations, it's probably going to be something similar to this. But the sheer fact that if it ends up being the same numbers, and we were able to get it through the Bekenstein-Hawking formulation, that would seem to give some credence to what perhaps Professor Maldacena was saying, and even some of the work from Bill and everything that's focusing on a thermodynamic perspective, because, I mean, pretty sure that's also Einstein, Professor Einstein, kind of noticed Brownian motion and therefore provided evidence for atoms and stuff. So occasionally they'll say Einstein invented atoms. Oh, is that all you did, good professor? God, must have been a Tuesday. All right, let's see. Right. Talking, metric is an absolute. It's discovered or invented. The metric is, I think, an assumption there. It's probably a very strong assumption, perhaps. I don't know. Charging chirality. Well, that's the interesting thing, because at some points we break chirality. Oh. That the whole CPT symmetry where we saw within the weak force there apparently was some symmetry breaking? Is that how we fully even justify the Higgs? Or I think Peter Higgs and Robert Engelhardt, I think Higgs, Engelhardt, Broward, I think they invented that before the Madame Wu experiments. Huh, I don't know. I'm gonna have to put up some history on some of this and do some research on that, just because I'm like, all right, I'm literally just realizing this right now. I'm like, All right, well, if there's a breaking in symmetry and there's a quote-unquote preferred direction, again, once you specify, why do we seem to have a left-handed bias in our realm? I don't know. The Higgs seems to help break symmetry and helps keep things nice and together there. I don't know. Well, let's see. Bill's conjecturing antimatter is when a photon flies near a nucleus and borrows spin. It creates a matter-antimatter pair. Okay, that's an interesting conjecture there. So it's a lot of times when we specify, and there's some interesting things, because what is if you take like the Hubble radius, you cube it, and then you divide it by the mass in the observable universe and multiply it by the Hubble time squared, you basically get like the Newtonian gravitational constant. It matches big G like really well. So, I mean, that's a cool thing. I mean, maybe that literally is. Let's just see this. This will be the last thing. I'm sorry, I'm going over here. So, was it? I think they used Hubble. Hubble radius cubed divided by universe total matter, and then I think it was Hubble time squared. That was something like that. It might be probably off by like a factor, but I think it's about magnitude. Hold on. That might work. I think I'm asking it too many questions. Let's just do this universe matter. Total. Should probably say observable. Oh, excuse me, mass. Derp. Okay. See, user error there, universe mass. Okay. Yeah, so you can see there, if you had the parameters there, it gets the first couple of digits because the Newtonian is like 6.67. So that's a cool little thing. So if you divide it by the Newtonian gravitational constant, it ends up being okay. It's obviously rounding right there, but okay, yeah, you're taking the Hubble length cubed divided by, because basically it's big G is Planck volume, Planck mass down there, and then Planck time squared. So yeah, it's saying one, but it's not, because I was gonna say, did I misremember the Newtonian gravitational constant that much? I hope not. All right, yeah, 6.67. All right, yeah. So, but as you can see, it's of magnitude and with rounding. I mean, that's a fascinating coincidence right there. I've seen papers like that, but it's okay. Now, maybe that holds throughout everything. Maybe it is, but I mean, is that much different than using like the Planck force as a constant of proportionality? I think it's generally the same concept. And the sheer fact, I think like Holly was saying, like some of these different relationships, it's amazing. And this is what really, really fascinates me. Okay, fine, Holly. Yes, cows are a multi-hole toroid, though. Just saying. All right, have a good night. Hey, Jiu-Jitsu Blev. Okay. Actual scale by to the Leech lattice. Ooh. Well, I think Thad's talked about that. I met Chris over in Portugal. He's a very nice guy. Very nice guy. He's been through a lot. Some of what he showed there kind of resonated with me. I'm like, I'm not sure he was doing a particular method, but there are interesting things when you go into different magnitudes and scales. And again, I view them normally as, oh, here's a happy little coincidence. Can I claim more? You would need to have some pretty rock solid explanation for what you're doing there. Doesn't mean it's not true, but it is interesting. So I'd like to, yeah, no, I'm just going to end this thing here. Just send a leave it in the comments, or shoot me. My email should be available here, on Twitter, friggin' whatever. Just remind me. I can go take a look and kind of go through, and we'll see what happens. But all right. Jax, I don't think I can help you there. It's like, I'm not Kevin Smith's dad. It's one of the things I've learned. Just we'll end with this: is if people are going to spend the time to visit you and everything, you got to be careful. It's usually not a good idea to attack your audience. It's just, it never seems to go well. I don't have to agree with my audience, but it's like, hey, your audience is your audience. They're all individual human beings with their own unique perspectives. Who am I? I'm just some crazy person on the internet that's rampantly speculating about things that are way over my head. But you know what? It's fun to do. If there's one thing that I've learned, it's everyone just really wants to be heard at some point or another. That's really, I think, what a lot of the stuff comes down to. Is just treating other people like you would want to be treated. I don't know. It's almost like they should make a rule out of gold or something, silver too. I don't know. But with that said, thank you, my friends. Peace out, everybody. We should have some more interesting stuff and things going on, and hopefully maybe get a few more live streams with some other folks to chat about some interesting stuff and things. But with that said, peace out, everybody. Take care of yourselves. Here's home for a better tomorrow.